Okay, we are in section 510, and this section going to be like a story problem where all you have to do is end up writing your own integral problem. And I'll take you through the first one step by step, and you're going to see how the rest of them run the same way. So the first one we're going to do is problem number 1. And I'll read this problem to you. It says it's a displacement problem. Suppose you take a long trip. You are impatient to arrive at your destination, so you gradually let your velocity increase according to this equation. So keep your eye on labels. This is a velocity equation where velocity is in miles per hour and t is in hours. Your displacement or distance equals velocity times time. Velocity times time equals distance, and if we're going to multiply those, that's doing antiderivative or area under the curve or integral. So we're going to take you through step by step. So we'll start with our velocity equation is 55 plus 12 times t raised to the 0.6. And our velocity is in miles per hour, and time is in hours. Okay, the graph. So the first step, it says sketch the graph. So in that, they actually give you the graph. And it kind of looks like this. You just keep creeping up. Your velocity keeps increasing and increasing and increasing. So here's our velocity, and here's our time. And what step 1 says is, on the graph, draw a narrow vertical strip of width dt. So we're doing a rectangular region. They're calling this width dt, the change in time. And dt is change in this variable, so change in time. Show a sample point TV on the graph. So somewhere in here we're going to pick an x value or a time and let that corresponding velocity value be our height of our rectangle. So that's going to give us our height. So that point is some generic t with its corresponding velocity. All right. So that's the first thing, is just drawing that rectangle. So then part B explains that the distance you go in this interval is approximately equal to the value of v, so the height, times this with the cross here. Write an equation for dy, the number of miles you go in dt hours. So the dy is equal to our velocity multiplied by time. Well, we have any, so I wrote the words out. Now we're just going to substitute. Velocity is given by this equation. So dy equals 55 plus 12 t to the 0.6. And our time is this generic width here, dt. Okay, that's part B. That's writing your equation. Part C is asking you to write a Riemann sum for your approximate displacement y between A and B. Riemann sum, now we're going to say, well, if I go from time A to time B, I'm just going to add up all of the rectangular regions in there. Riemann sums are rectangles, so it's the sum from A to B of my distance equation. 55 plus 12t to the 0.6 dt. Now D says write an expression for the exact displacement you go by adding up all of those areas. Well, the exact is just flipping out the summation of the rectangles for an integral from A to B of 55 plus 12t to the 0.6 dt. So they're trying to take you baby steps through here and people get totally confused. But look at what we've done. It hasn't been complicated. All we're doing is writing an integral for the area under the curve by making you write out that velocity times time is displacement. We're doing the sum of the rectangles with the Riemann sum, which is done more accurately with just doing antiderivative. Okay, now here's the real question. Now that you've got your integral, part E says, how far did you travel in the first hour? So how far in the first hour? Well, if you think about it, that's the area under the curve from time 0 to 1. We want that area will be the distance, because velocity times time is distance. So we're just going to go 0 to 1 of this equation. So now we just do our antiderivative. So the 55 goes to 55t plus, keep the multiplier of 12. We're going to add 1 to that and then multiply by its reciprocal, which is 1 over 1.6. And then we're going to evaluate it from 0 to 1. Okay, well, plugging it top minus bottom, plugging in the 1, that's going to give us 55 plus 1 to the 1.6 is 1 times 12 is 12, and then times that, I'm going to need a calculator. Let's see. So it's going to be 12 divided by 1.6, 11.32. And then minus, putting in a 0, that'll give us 0, plus 0 to the 1.6, 0 times 12, look, that all zeros out. So we are getting, what is that going to give us? 55 plus 11.32, 66.32. Miles. Okay. Oh, wait, what happened there? Oh, this didn't work out right. I don't know what I divided by. I have to go back up there and see. Oh, 1.06. Oh, this number's not right. I put in 1.06. It is actually, I was going to say it didn't match what I had in my notes. 7.5. My bad. Let's see. So 55 plus 7.5, we got 62.5 miles in the first hour. Okay. Second question says, how far did you travel in the second hour? So it's still on part E. How far in the second hour of travel? Well, you got to think about, where is the second hour of travel on your graph? Between what two values is the second hour? Well, the second hour starts after you've completed the first hour. So from 1 hour to 2 hours would be my amount of travel in the second hour. So interpreting this question and finding the boundaries was the challenge here. So how far in the second hour? It's going to be the antiderivative from 1 to 2 of that same equation. It's going to have the same antiderivative. I've just got to change my boundaries to 1 to 2. So 55t plus 12t to the 1.6 times 1 over 1.6, evaluated from 1 to 2. So if I put in the 2 first, I'm not going to try to do that all in my head. I messed it up last time. So 55 times 2 plus 12 times 2 raised to the 1.6. All of that divided by 1.6. So 132.74 minus that 62, let's see, when I put in the 1, I get the 62.5. $70.23 miles. Where is it? Where? Oh, yep, matched my answer. Couldn't find it. 70.2 miles. Okay. And then on to part F. Part F asks for how fast were you going at the end of the second hour? How fast at the end of the second hour? Well, how fast? I think that's a velocity. Well, that means I've got to give a velocity answer. Here's a velocity equation. All I've got to do to get a velocity is plug in a time value. Well, if I am at the end of the second hour, what do you think you're going to put in there? The end of the second hour is at the time we're starting hour 3. So we're going to let t equal 3 and plug it into the velocity equation. So keep track of the equations. So 55 plus 12 times 3 raised to the 0.6. Just a plug and chug. Let's see. 55 plus 12 times 3 raised to the 0.6. Okay, I'm getting 80.13 miles per hour. Double checking. Oh, I did type it wrong. Having struggle bus here. 78.2 miles per hour. Okay. And there's still one more question. Oh no, that was it. How fast? Okay. So let's take a look at what we did. I'm going to write down the steps for you, because they're going to guide you through almost all of these steps again. So the first thing you want to do is sketch your graph. Don't know what it's going to look like, but I'll just use the last one for an example. They're going to ask you to draw that narrow strip and pick a point. So if this is X and this is Y, you draw a narrow strip. they're asking you to pick an x value in here and when you plug it into your function, let the corresponding y value give you the height of the rectangle. So you've got an xy ordered pair in the strip. Number 3, they have you write the equation for the area of the rectangle. And the width of the rectangle, that point is x, but the width is called dx, the change in x. So write an equation for the area of the rectangle. So the area of the rectangle, the height is going to be given by your y value from your function. The width of the whole rectangle is dx, the change in x. That's going to represent your area of the rectangle. And for us on the last one, because it was velocity times time, that area represented distance. And that might be changing. When you multiply the two x and y together, it might be work, it could be distance again, we'll see. It may be changing from problem to problem. Then they ask you to write a Riemann sum. And all that is taking your multiplication here and putting that sigma, that summation in front of it. Then your 5th step asks you to write the exact area. And that's just flipping out the summation for your integral. I mean, I should be using f of x here, but y is the same thing as f of x. And then somewhere in the problem, you're going to be answering the questions now, putting the boundaries on, find boundaries for the question. And then start answering the questions. But that's it. Don't get caught up in all of this that it's confusing. It's not that bad. Draw the rectangle. The height is your function value. The width is your dx. Write the sum symbol out in front. You might have boundaries here, the a and the b. Then you flop that out for the integral symbol for the same boundaries and answer the questions. That's it.